Good afternoon. I'm going to discuss the acoustic aspects of distributed electric propulsion design. But more importantly, as part of this, I'm really excited about it, is a new way that we can introduce acoustic constraints and requirements into the design process. And this we really look as an enabler, and the distributed electric propulsion system has allowed us to exercise this. And as you will see, I think you'll get excited about this as we are on the team. Before I get started, I want to acknowledge particularly the Aeronautical Sciences Project. A lot of this work started about 2 years ago for us to get perception influence design, that means the acoustic aspects of it, into the design process. And without performing this as part of the cross-cutting tool development under that system, we wouldn't be basically where we are today. This work is continuing under the Transformational Tools and Technology Project into FY15, and I've listed here some of the key Langley participants to date, and we hope that as you see this presentation and some of the other ones that were given today, that you'll also want to see solutions to part of this and start to contribute to part of these. By no means have we solved a lot of the problems here, but I think we've made a great leap, and we've kind of jumped into the next way of paradigm of looking at things, particularly for the design for acoustics. So first I'm going to kind of introduce what we mean by perception influence design, and then go into an application where we've applied it to distributed propulsion, and then kind of outline some of the current opportunities that we see, and I'm sure you'll see other ones as you absorb what I'll be presenting here as far as acoustics. And that's what we're really excited, because it's wide open of what we can do. As Mark's mentioned, distributed propulsion really allows us a lot of degrees of freedom that we didn't have before with some of the conventional designs. So looking at an aircraft, particularly one like this, it looks a lot different. It doesn't have one propeller. It's got 18 of them across here. But our typical, when we look at this for acoustics, there's a lot of things on here that influence the overall aerodynamic design, the fuels and emission, the mission that acoustics do drive. And typically what has been done in the past, they design it for all of that and then it's handed over, and acoustics has always been deemed as a barrier. I want you to start thinking of acoustics as an enabler. So having acoustics as part of the design cycle, we can at the early stages, so that it's not a surprise in the end that this thing doesn't get certified or is not acceptable, we're influencing it at the beginning. So when they come up with designs such as this for a new high lift, which is not your typical slat, we got propellers here. How does that affect the acoustics? So as part of the design of even the propellers, as Nick alluded to, acoustics had a strong influence of how those were designed, particularly on the tip speeds, where you want to stay away from, and how the propellers themselves, each of the blades were designed. In addition, for the overall aircraft, the landing gear. That's a well-known noise source, particularly on approach. And the integration of that into the airframe leads into how you would do that on the structural aspects as well as the aerodynamic for lift and drag. And what I'll concentrate on here is the propeller system. The propeller is probably the main component on a vehicle like this. You got 18 of them, and how that's integrated into the vehicle, and what does that happen in terms of the noise? Because when you hear a propeller aircraft fly over, you typically hear the propeller, particularly at higher altitudes. So what do I mean by perception influence design? Well, typically, in the green box going up and down, that's kind of our multidisciplinary design cycle. It's not in a cycle, but these are all the elements: aero performance, fuel burn, emissions, controls, structures and material. That all works to pull out a viable design. Part of that is system noise, and that's usually put in as a cost function, and there's certification metrics that usually provide guidance for that. To get the system noise at the system level, you got to be able to predict for the components. For a distributed electric propulsion, that's really stressing and a challenge for a lot of the acoustic tools that we have now. For the props, we got prop-prop interaction. We don't have an isolated prop on the beginning. And then the integration of that into the wing, what additional sources are we creating? Particularly the downwash of the propeller will increase trailing edge noise. So we have a lot of challenges still remaining in that, but we're able to get the cost function for noise within the design cycle. Okay, so if for some of these unconventional ones, particularly this, how will this be perceived by people? You know, how will this have the same annoyance factors? So as part of this work, we have a human perception aspect. So not only will we create the regular metrics that you see as numbers, but through oralization of somebody actually hearing it, how do we perceive that different from another aircraft? For instance, is some of these aircraft may not sound like any propeller. It's kind of distinguishing between, you know, if you have multiple ones, they may be out of phase, and so it might sound like a rough riding lawnmower. Even though it might have the same overall noise metric, one may sound much more annoying to the other. So to explore that, we're developing tools to create the human response. And so I'm going to give several demonstrations here where we've actually oralized some of the configurations for this distributed propulsion system with the propellers. The very first obvious one is to look at the difference between a single prop, which you're used to hearing, and one where we've included 18 props. So just on a metric, running it through our predictions and looking at it on paper, going from 1 prop to 18, we have the overall thrust is maintained, but we were able to reduce the overall sound pressure level by about 12 dB. For those of you not used to dBs, a 10 dB reduction is, you'll say that it's perceived as being half as loud. So that is very, very significant. So these are all done at the same thrust. So once you reduce the level, other things that can happen is with a multi-prop system, as I mentioned, we have a lot more degrees of freedom. Each one of those props don't all have to be rotating at the same speed. We could alter the prop at different speeds because it's the tonal content that you hear, the blade passage frequency. So by changing the RPM slightly, we're going to change the blade passage frequency slightly, so you're going to have main tones that are not all at the same frequency. So how would that sound, and if they're all in concert with each other? Another thing that can be done is we can have the props rotate at the same RPM, but they're phased differently. So it'll have a diffraction pattern, and you'll hear it differently than if they were all phased. All the blades were phased in the same manner. Another thing that can happen is we could rotate them in different directions. All these 2 through 3 we can all do maintaining the same thrust, but as you'll see, they could have a significantly different acoustic character to them, and I'll leave it up to you to determine how annoying or less annoying they are. So the very first one, before I go on here, sorry to back up, but I'm going to show a single prop to kind of the baseline of it, and then I'm going to explore just only the second one, the spread spectrum. I'll show 2 examples where we differed the RPM. One set will be they'll just changed by 10 hertz between the blade passage frequency for each propeller, and then the other one I'll make it much finer. They only vary by like a half of hertz. And so you're going to see how sensitive the noise is to that, and also relative to to a single prop. So the very first one is just your general aviation prop. I might add these predictions were only made just including the tonal component. The tonal component in our predictions. We did not include the broadband, so that's some of the things that we're developing further in our tools. But so let me play this here.
I turned the volume down, so you may need to turn it back up, Steve.
So to me, it sounds pretty much like a general aviation flying overhead. This is all done purely from prediction, just includes the tonal component. Now the next example, we're going to take the same one. We have all the propellers, 18 propellers, and they're all spinning at the same RPM, and they're all phased. So you're going to see the difference between one blade, or one propeller, and 18 propellers. And this is relative to the first one, so. Okay, so this was 12 dB less than the first one that you heard. And kind of general rule of thumb, that should have sounded about half as loud. But you notice the character is much different. even though the levels were that significantly that less, your perception of the noise, whether it's acceptable or not, changes. Now, the next one is going to be these same 18, but now each one of them, the blade passage frequency has changed slightly, and they're off by 10 hertz. So let me move that one. So the overall sound pressure level between this one, the second one, and the third one is the same. It's the character that's changed, and it's spread. Now, when I say overall sound pressure level, that's like over a volume. So this was for an observer directly underneath. So it not only changes the level, it changes the directivity, and it changes the character. And then the last one is, rather than 10 hertz, they're just only slightly. It's only a half a hertz apart. So let me go to the next one. Whoops. So these last two are just changing the RPM. So through controls, as Irene will speak, having controls over a multi-prop type of system, we can almost tailor the noise for something like this. We can make it sound hopefully something like Beethoven versus a chainsaw. But for the same overall sound pressure level, the character of it has a huge impact on how you perceive that noise. All these were done for the same sound pressure level, and your perception of it, I'm sure, was different for each one. So where do we go from here? One of the other aspects is, this was just kind of an anecdotal, you listening to it in the audience, but how do we actually measure this type of annoyance? What kind of metrics would we come up to describe it? So there's a laboratory that's been developed here at Langley. It's over in building 1208. It's an interior effects room where we can actually take these oralizations and play them to in a scientific way. We bring people in that have been screened, and we conduct sound jury type of testing to truly evaluate the annoyance of these. And hopefully this will lead either to help develop new annoyance metrics or new cost functions that are within the design, particularly for aircraft that we don't know anything about. Some of these new designs that Mark showed to. We find this very exciting. This just opens up a whole new world of how we can explore this for the design that's all tightly coupled with the aerodynamics, the structures of material, and now the noise within these systems. So in closing, we can shape the noise through design, configurations, and operations, and I've showed you some dramatic effects here. The perception influence design type of scenario that's been developed and now kind of in place and just kind of on its infancy. There's still a lot of work to be done in the fidelity of the tools, the human aspects, the human response to it, but we have a capability that's just on the brink of just opening a whole wide world of aircraft that we can look at, in the design space before we actually build. Some of the opportunities I've listed here is immediately we can reduce the noise through multi-props. We could tailor the noise, as I've shown. How does this impact the opportunity that we can make noise exposure, particularly if these things are landing in small airports in populated areas? This supports the spiral development, not only for the DEP, but across all aircraft classes. We've demonstrated it for this small GA aircraft. And some of the main challenges is how do we continue this integration into the multidisciplinary design space? What are the acoustic prediction fidelities that are required, and what tools don't we have that can truly evaluate this before actual hardware is built? And how does this relate to certification? And then single event versus fleet noise. I showed you a single event, but how does this work in concert when you have a whole fleet of these or a swarm of them acting? So that's the closing remarks.